And then I think this that we are having might be a thing of the past. But in any case, I just want us to at least do something so that we don't lose all the time completely. Okay, so to start with, I just want to go through the main points in the lesson that we had last time. Okay, so before I go, before I do that, did you guys see the video? The video recording of the last class?
Yes, we did, sir.
Okay, any issues from there, or maybe any questions or concerns or anything coming from the last meeting that we had? Anything? Okay, so there's nothing. Please let us be interacting, because I think I'm only hearing one person respond. So I'm not really sure if everyone is together with me. So I would appreciate it if you give me the feedback. In any case, let us proceed. So we are looking at the electric field, how the electric field behaves in conductors last time. And then what we said was that if you have this as a conductor, and then on this conductor, if you place, the first thing is that in a conductor, the electric field at the surface is always perpendicular. It's always perpendicular to the surface at that particular point. So you see, this is the surface of a conductor. I think we convinced ourselves that the direction of the electric field must always be perpendicular to the surface of the conductor at a particular time. So that is one key point that came from the last class. Okay. The other point that we learned about was that if you have a cavity, is that if within the conductor, the electric field will always be equal to 0. The electric field will be equal to 0. If you make a cavity, inside the conductor, then the electric field will also be 0 inside that cavity. Okay, the next point that came out, so this is just a demonstration. You see, if you place the charge in an electric conductor, the charge will go to the surface. I think we discussed this at length. Okay, and then the other thing was that in a conductor, the charge is distributed in such a way that it is concentrated on the edges of the conductor. If the conductor has got some sharp edges, then you expect that there will be charge, there will be a high charge buildup in those areas. Okay, I think we explained all these points, but then we ended on this very interesting note. We ended on the very interesting note, so that, of course, we know that within the cavity of the conductor, the electric field will be 0 if this charge were not present. But what if we introduced a charge inside the cavity of a conductor? What will happen? What will be the behavior? And then at that point, the main thing that came out was that there will be another charge that will be induced. Because of this positive charge that is enclosed in a conductor, it will induce a negative charge around, and then we convinced ourselves using the argument of Gauss principle that there will be a charge that will be induced there in such a way that inside the cavity, there will be an electric field. Inside the cavity, there will be an electric field coming from this positive charge that is enclosed and the other charge that has been induced there. And secondly, this charge that has built in the inner surface of the shell will leave the positive charge that is exposed outside. And that positive charge will again result in an electric field outside. So with this arrangement, we see that inside the conductor, the electric field is equal to 0, but within the cavity, there is an electric field, and outside the cavity, outside the conductor, there is an electric field. Okay, so now, what if we move this charge that is inside there? We try to try to move it. Have you seen what has happened there now? I think this, I want to get feedback from you. You see what has happened was that the charge was at the center within this cavity. Now what happens when we move the inner charge off center, so that we move it slightly away from the center like that? What do you think will happen to the electric field inside as well as the electric field outside? So let me get some input from you. What do you think will happen? Let me see hands. Hello? Hello? Are you guys able to get me?
Yes.
Okay, so I have a question. What do you think will happen to the electric field pattern if you move this charge off center? Okay, so Mr. Chipo Katito. Okay, so let us give it to, yes. I can see Mr. C.
I think
There's hand, but just wait. Let us first give it to Chipo.
So I think the electrons which are on the cavity, since when the charge moves to this side, the side where the charge will move, the electrons which are on the cavity are going to move there, since the distance between the cavity, the electrons on the cavity, the distance has reduced. So the forces will be stronger on that side.
Okay, so what you're saying is that the charges will be more concentrated on this side, right?
Yes, sir.
The charges will be more concentrated on this side because of the Coulombic interactions, right? Between this positive charge and this charge, right? That's very good. That's very good.
Yes, sir.
It's actually true. Now, what do you think will happen to the electric field pattern inside there, inside this cavity? What will happen to the electric field pattern? Mr. Sinyenza, I could see your hand. Okay, yes, Genius.
Yes, me what I think is that the electric field in the cavity won't be equal because of as you can see there, the radius from the charge there up to the surface of the cavity in there, the radius are not equal. So the electric field in there won't be equal.
Okay, so it seems that we have lost. Hello?
Hello, sir.
Okay, so let us see now what happens. So what will happen is this. So of course, since you have a positive charge here, this positive charge is going to induce the negative charge as before. But as Chipo already mentioned, that you see that this charge is off center. It is closer to this side than it is to this side. So what will happen is that the charge will be more charge build up. More charge will be induced on this side, okay, than on this side, okay, because this charge has been moved off center. And now the electric field inside the cavity, you see the electric field inside the cavity, it will be kind of distorted. There will be some sort of a distortion in the electric field. Why is this distortion there? You know that the electric field must always be perpendicular to the surface of the conductor. We learned about that. The electric field must always be perpendicular. So the this electric field will be distorted because this one needs to bend very quickly so that by the time it is reaching the surface of the conductor, it must be perpendicular at this point. This one will bend, but not very much, such that by the time it is reaching here, it must be perpendicular to the surface of the conductor. So there will be that kind of a distortion inside the electric. So there are two things that we have noted. First of all, the arrangement of the electric of the charge on the surface, on the inner surface of the conductor is such that on the side which is nearer to the charge, there will be more charge. There will be more charge on that surface than on the surface where the charge is further. Secondly, the electric field lines will be distorted in such a way that they are always perpendicular at the surface. Okay, so now what will happen outside? What will happen outside the Gaussian surface? Okay, so in order for us to find out what will happen outside the Gaussian surface, this is not the Gaussian surface, what will happen outside the conductor in this region that is here? How will the electric field be affected by the fact that you have moved this charge off center? Okay, so in order for us to understand what will happen, let us draw a Gaussian surface inside the conductor. So we draw a Gaussian surface somewhere here inside the conductor so that it covers all this, it encloses all this charge that is here. Okay, so that is the Gaussian surface. It covers all the charge that is here. Okay, so now what can we say about the charge? What is the total charge that is enclosed by this Gaussian surface? What is the total charge? Anyone? Anyone to say something about the total charge that is enclosed? What do you think is the total charge that has been enclosed by this Gaussian surface that we have drawn? Hello? Okay, then I'll try to explain. What has happened is that, the total charge that has, there is this positive charge, but then this positive charge has induced an equal magnitude, but opposite sign of the charge that is around there. So if you add this positive that is here and the negative that is around there, then you get the zero. Now remember from Gauss law, it says that the product of the electric field and the area, if you like, will just give you the charge enclosed over epsilon naught. That is Gauss law. Now, if the charge enclosed here is equal to 0, you see that the charge that is enclosed by the Gaussian surface there is equal to 0, then what do you expect the electric field to be? What do you expect the electric field to be? The electric field will be 0 inside. The electric field inside the conductor will be equal to 0. So what does it mean? Since it simply means that this charge here, the electric field due to this charge has been shielded. It has been shielded by the conductor because of this charge that is induced in the inner surface. So it means that the charge that is the electric field that is produced by this charge here cannot be felt, has got no influence on the electric field that is outside. So it means that the electric field that is outside will just be the same as before. The electric field that is outside will just be the same as before. So let us go through the argument again. We drew a Gaussian surface. We drew a Gaussian surface around like this. We drew a Gaussian surface around like this. And then from the Gaussian surface, we concluded that the net charge enclosed was equal to 0, Since the net charge enclosed was equal to 0, it means that using Gauss principle here, the electric field is equal to 0. Okay, so what does it mean? It means that the inner charge, this inner charge it is completely shielded. Its effect cannot be felt outside this conductor, and as a result of that, the electric field will be just the same as before this charge was moved. Any questions? Any questions? Okay, yes, Frederick.
But what would have happened if the charge inside wasn't shielded?
Okay, your line is really breaking. I don't know if it's just my system, but I can't get you properly. The line is breaking. Come again.
I'm saying that what if the charge inside wasn't shielded?
If the charge wasn't what? If the charge wasn't what?
Shielded.
Okay. Can you type your question?
He's saying if the charge was not shielded.
Simply saying that.
Okay, if the charge was not shielded. Oh, okay, I now understand your question. What if the charge was not shielded? So that indicates that maybe that point has not been, my explanation was not good. Okay, what is making this charge to be shielded? If I may ask. What is making this charge to be shielded? Anyone? Anyone? This charge here. Okay, so this charge.
I think.
Yes.
I think it's because of the negative charges which has been induced.
Yes.
Because when you talk of the total charge enclosed, they are going to cancel because this charge here, the positive charge, has induced the opposite charge but of the same magnitude.
Okay, so that's exactly. Have you heard Mr. Chip? Within this conductor, within this conductor, by virtue of us placing a positive charge there, these negative charges have been induced around here. They have been induced in the inner surface of the shell. So it is these electrons, if you like, these electrons that are around here are the ones which are shielding the electric field of this positive charge. You see, this positive charge is producing the electric field. Remember, the positive charge is the source of the electric field. The negative charge is the sink. Okay, so all the electric field lines that are emanating from this positive charge are actually being absorbed into the negative charge in such a way that it has got no influence on the electric field that is outside. So that's what we mean when we say that this charge is being shielded. Is that clear?
Yes, it's clear.
It's clear. Okay. So let us now move on to something else. So far, what we have just been talking about is the electric field and applying Gaussian law to a point charge. Here we are just trying to analyze Gauss law in the context of a point charge. What about if we have other charge distributions? You know, we had actually found that there are different charge distributions that you could have. So let us first start by looking what kind of a charge density is this? And don't worry, I'm trying to ask a lot of questions to try to engage you so that we move together. Because this is an online class, I don't want to be talking together. I don't want to be talking alone. What kind of charge distribution do you think this is?
I think it's surface charge distribution.
Surface charge distribution. Okay, so now let us try to see how we can apply Gauss law to a surface charge distribution. So I must mention that Gauss law is quite very important in helping us to find the electric field. So when we want to find the electric field at a given point, due to a certain charge configuration, be it a point charge or a continuous charge distribution, we can use the Gauss law as long as there is symmetry in that charge configuration. So now, if we have a surface charge distribution like this, remember we had talked about a surface charge density. Surface charge density is basically just the charge a unit area on that charge distribution, right? You remember that. So surface charge density, we denoted it by sigma. Okay. Now, from this equation here, you see that we can actually find okay, let us try to do this. So if you have this charge distribution, what kind of a Gaussian surface, can you think of that will be able to enclose some charge within this charge distribution? Okay, so the kind of before we come to the Gaussian surface, let us first of all look at the electric field lines. What kind of electric field lines are we going to have from this distribution? So the electric field lines are going to always be perpendicular. They're always going to be perpendicular to this paper. Imagine that this is a piece of paper where there is some charge that is smeared there. So the electric field lines are going to always be perpendicular to this piece of paper in this direction that is shown, right? Okay. So now, if you look at these electric field lines, you want to construct a Gaussian surface that will be symmetrical to these electric field lines. What kind of Gaussian surface can you think of? You can think of a cylindrical Gaussian surface, such as one that has been drawn here. Are we together? Okay, so now before we go further, let me ask another question. Why are we saying that the electric field lines must be perpendicular to this surface? Why have we concluded that the electric field lines must be perpendicular? No? Why do you think the electric lines will be perpendicular?
Area vector.
The area vector, what about it?
Repeat the question, sir. Sorry.
I repeat the question. Okay, so have you seen this? We say that this is a surface charge distribution, right?
Yes.
Surface charge distribution, I like looking at it like a sheet of paper. It's a sheet of paper on which some charges are placed. And assume that this sheet of paper is a conducting sheet of paper on which the charges are placed. Now, we want to find out what is the electric field pattern that is coming out from there. What is the electric field pattern? Are we together?
Yes.
We have said that the electric field pattern will be such that the electric field lines will be perpendicular to the paper. Have you seen that?
Yes.
The question is that why are the electric field lines perpendicular to the paper? Okay, so let's have that in mind. Let us have that in mind because we are running out of time, and then when we come back from the break, we're going to pick it up from there. Okay? When we come back from the break, then we're going to pick it up from there. Keep in mind that if you have a conducting sheet of charge, then the electric field at any point will just be given by sigma, which is the charge density, the area charge density over epsilon. Now, can we use the Gauss flux theorem in order to calculate the electric field of a line? Do you remember that in one of the lectures, we had actually used Gauss law to find the electric field, field along line of charge. Well, how can we apply Gauss flux theorem when finding the electric field along a line of charge? So the principles are the same. Let me just now talk about the steps that we take. If you have a line, if you have a charge density, the first thing that you do is you decide on what is the Gaussian surface that I can take. After deciding on the Gaussian surface that you can take, then you apply Gauss flux theorem. I think I want to explain a little bit further on this one. Let me just create a blank slide. Let me create a blank slide. Okay, so before we proceed, I think I just have a feeling that people are not still very clear on this Gauss flux theorem. So this is very, very important. So I have to repeat. So remember when we are talking about the point charge, right? About the point charge, if this is a point charge, it is Q. The first thing you want to apply, you want to find the electric at a certain point, at a certain distance that is R. You want to find the electric field at a distance R away from this. So what are the steps that you are supposed to do? The thing is that first of all, you have to draw the electric field lines that are coming out. So you know the electric field lines are coming out like this. This is the electric field lines. So the first step is that you draw the electric field pattern. The electric field pattern. What is the next thing? The next thing is that you look at the electric field pattern and ask yourself to say, looking at the symmetry, which Gaussian surface will allow me to calculate? You must have a symmetrical Gaussian surface which will pass at the point where you want to calculate the electric field. Are we together then? So in this case, we considered a spherical Gaussian surface. You add on the drawing. We considered a spherical Gaussian surface, assuming that the distance from here to here is actually R. And then we were able to apply Gauss theorem. See, Gauss theorem says that the electric flux that is passing the Gaussian surface must be equal to the charge that is enclosed by the Gaussian surface over epsilon naught. Basically, that's what the Gauss flux theorem is telling you. And then what is the electric flux? The electric flux is just written as this integral of E and then dot dA. You must understand what dA means. dA in this case is a small area. It's a small area that is is a small area where the electric field lines are passing. So this is a dot product. So what it means is that it is the magnitude of the electric field times this dA, and then times the cosine of the angle, between the two. Times the cosine. So I'm still just trying to work with the electric flux. Are we together? So now you must understand what is my theta. That's the next thing to ask. The theta is the angle that is between the electric field and the vector that you have, the area vector that you have. Okay, so almost always you are going to find that the angle might either be 0, this might either be equal to 0, or it might be equal to 90 degrees. So if you find that it is 0 degrees, then the cosine of 0 will be equal to 1. Then this one can just be written as the electric field times dA. If it is 90 degrees, then the cosine of 0 is the cosine is equal to 0. So the electric flux will be 0. Now, on the other part, you just have to ask yourself, what is the charge that is enclosed by this Gaussian surface? What is the charge that is enclosed by this Gaussian surface? So those are the steps that we are taking. Let me go back and then just review on what we have done. So here we had this, I don't know if I'll be able to draw it properly. Let me just try. So I have this. Okay, so so I have this this surface, and then on this surface I have some charges that are distributed uniformly. Some charges that are distributed uniformly. Okay, and then the other thing that I know, I must draw the electric field lines. What are the electric field lines? I know that the electric field lines are going to be in this direction. The electric field lines are going to be in this direction because they must actually be perpendicular. Remember, I had said that since this is a conductor, so the electric field lines must be perpendicular. Okay. So the next thing that I now have to think of is that what kind of Gaussian surface am I going to draw in such a way that these electric field lines are going to pass through some sort of asymmetrical area. So in this case, we discovered that we can actually draw a what? We can actually draw a cylindrical drawing can be a bit challenging. So pardon me, I'm trying my best. So you can actually draw a cylindrical I hope that we are making sense here. So this basically is the Gaussian surface. Now the question is that, you see the Gaussian surface, you know that the Gaussian surface, a cylinder always has the curved area and it also has the cross-sectional area. So you see that the flux, the only place where the electric field lines are passing, is this one here. On the curved surface area, there are no electric field lines that are passing. Why? Because the curved area is perpendicular. This is at 90 degrees. The curved area is at 90 degrees for the electric field lines. You know, the cosine of 90 will just give you 0. So there is no flux that is passing there. You can even see it because there are actually no electric field lines that are passing there. So if we apply Gauss flux theorem, then we are saying that the electric flux must be equal to the charge that is enclosed. The charge that is enclosed. The charge that is enclosed where? By the Gaussian surface. The one that I've drawn in yellow here is the Gaussian surface. So the charge that has been enclosed by the Gaussian surface is equal to the electric flux, the flux that is passing through that surface. Okay, so now when we talked about the electric flux, we say that this electric flux can be written as the electric field itself times the dA. Now, where is the dA? I mean, the area that we are talking about is this one. This is the area that we are talking about. And we have assumed that this area can be broken down into small areas, each of which we are calling it dA. Okay, so now you can see that this can be written as the electric field times the dA times cos theta, where theta is the angle between the dA and the electric field. So we were able to see that the theta in this case is nothing but 0, because you find that the area vector to this is in the same direction. The area vector is in the same, remember the area vector must be normal to the area. So the area vector is in the same direction as the electric field, so the theta is equal to 0. So in short, when you try to evaluate, follow all those steps, basically we just come with the electric field, which is this one here, times when you integrate this area, you just come up with E must be equal to this charge enclosed. By the way, I think I forgot to put the epsilon naught here. So I must have the epsilon naught, and then is equal to the charge enclosed. Now you have to express this charge enclosed in terms of the surface charge density. You see that this charge enclosed here is nothing but, so the charge enclosed is basically just nothing but the surface charge density times the area. Remember from what we had learned before, surface charge density is just equal to the charge over area. So if you want to make charge subject of the formula, you just cross multiply there. Then the charge is just area times the sigma. So it means that this, remember very well, we just had E, and then times that times A will just be equal to this sigma times A. Now this A is the same as that A. And then that is basically how we had arrived at this result here. Okay, so in a similar way, I think let me get some feedback from you before I proceed. Are we beginning to make sense of these things? Let us chat. Are we making sense out of what we are saying?
No.
No? Okay, no. I think I've heard the no. Okay, let me hear what others, let me get the input from others. Are we making sense?
Hello, sir.
Huh?
I only have one question actually. Why didn't we consider?
No. Before we come to that question, I think I need to know whether we are making progress. So, others, are we making sense?
Yes, sir.
Right. Okay. Okay, now that. Pardon? Okay, then let me get the question. Someone had a question?
Yes, sir.
Yeah.
Why in the same didn't we consider the area of the cylinder, since we use the cylinder as our alternative?
As our Gaussian surface.
Yes.
So the question is what?
Why did we use for the GA? Why didn't we use the area of the cylinder?
The area of a cylinder. That's a good question. What is the area of a cylinder? What is the area of a cylinder? What is the formula for the area of a cylinder? What is the formula for the area of a cylinder? Do you remember? We have, if it is a closed cylinder, then we have the area of this circle here, which is pi r squared. The area of this circle also that is behind, pi r squared. And then the area, the surface area of the curved part. Not so. How do you calculate that? If you remember very well, it is 2 pi r times the length.
Yes, sir.
Remember this formula? You remember this formula, right?
Yes, sir.
So now let us hear the area. What we mean by the area, we mean the area where the electric field is passing. The area that is making up the electric flux. Remember the issue of electric flux. The electric flux is really where the electric field is passing. Now, if you look at this surface area, the surface area here, are the electric field lines passing in the curved area? Do we have any electric field line passing through the curved area? We don't, right? Huh?
No, we don't.
Pardon?
We don't have any.
We don't have any electric. So in which area are the electric field lines passing? Do we have any electric field lines passing through this area? Do we have any electric field lines passing through there? We also don't have. So it means that this is not there. The flux through this is equal to 0. The flux through this is equal to 0. We only have the flux through this area here, which is the pi r squared. So in this case, we can even, when we talk about this area here, we are only talking about the area where the electric field lines are passing. And in our case, specifically, we are talking about the area of this circle here. Because at the back here, no electric field lines that are passing. And then on the curved surface, there is no electric field that is there. Are we together? Was your question answered?
Yes, sir.
I just have a question.
Yes,
what of the length? Are we not going to consider the length?
Why are we going to consider the length?
Why are we not considering the length from where the electric field is passing?
Someone attempts to answer that question. Madam, I'll hear your voice in the background. To make your Gaussian surface.
Are you here?
Here a plate.
Hello?
Hello, sir.
Okay, so the length from where to where? The length of the cylinder?
Yes.
Okay, why do we want to consider the length of the cylinder? You know, we talk about the flux. We are using Gaussian flux theorem. So we must consider the area where the electric field lines are passing, because it is only when the electric field lines are passing through a certain area, that is when we can talk about the flux. So you know, don't talk in terms of the length, talk in terms of the area. So I've explained to you that in this case, we have 3 areas. We have 3 different areas. We have the area, you know, imagine this is a cylinder. We have this area, the front area. We have the back area. And we also have the surface area around. Now, that surface area around, if you remember from your measuration in grade 12, then you realize that the surface area of that curved path is given by 2 pi r L. That is where the length is coming into play. 2 pi r L. Now, within that area, within that 2 pi r L, we don't have any electric field lines that are passing. In short, the theta is equal to 90 degrees. The electric field and that surface area is equal to 90. Are we together? So the flux that is passing through there is equal to 0. So that is why we are not considering the length. Have I answered the question? Okay, so I think my time again is finishing, and I'm sure I think even the 1 hour that we are given ourselves is almost up.